So hi everyone, my name is Julius Huijts. I work in Eindhoven in the Netherlands. And I realize my talk is a little bit different from the rest of the talks this week. So I'm definitely not a biochemist. I'm a physicist and I work on the development of a new type of instrument. But I hope that this instrument or this method can become part of the future of dynamic photobiology, and that's why I'm here. So if now you want to make your protein molecular movie, then these are the tools that you have available are, of course, the X-ray free electron laser or a synchrotron. I think you'll all agree that it's difficult to beat the temporal resolution of an X-vel, but the accessibility is not really great. For a synchrotron, the accessibility is a bit better, but you still need to apply for beam time. While the temporal resolution, you can do time-resolved experiments, but not with the same temporal resolution as at an X-vel. And then we have this here, a transmission electron microscope. And you can look at proteins doing crystallography, like people did in the 70s, 80s, basically before the advent of cryo-EM. And this instrument is obviously very accessible. All major universities, research institutes have such a TEM, at least one in the basement. But the temporal resolution, we'll see two talks on Thursday on time-resolved cryo-EM, where I think the record of Ulrich is that he goes down to about a microsecond. And as far as I know, nobody has done anything time-resolved on crystallography in using a TEM. Well, that would actually be great because then you have this tabletop instrument, and can we not combine this with a temporal resolution of an X-vel? That would be amazing. The reason that nobody has done that yet is that it would put very stringent requirements on the electron beam. So schematically, if this is my crystal and this is my electron beam, then I want to have a spot on the crystal that is roughly the size of the crystal. So that's typically a few microns to a few tens of microns. But if I do crystallography, I also want that beam to have some coherence. And the transverse coherence length needs to be at least as large as the lattice constant of my crystal, right? Otherwise, you don't get constructive interference. You cannot do crystallography. And for protein crystals, this lattice constant is typically several nanometers. And what that means is that limits the angle of divergence with which you can make your focal spot on your crystal. So basically, the larger your angle is with which you come in, the smaller your transverse coherence length becomes for a certain electron energy. And you can calculate that for certain parameters, that means that this angle here needs to be below a millirad. Now, in electron beams, the quality of an electron beam is described by the emittance. And for the laser, people that work a lot with lasers here, it is very similar to the beam parameter product. So this emittance is proportional to these two numbers that I just mentioned, the size of your spot and the divergence angle. And so you can calculate that in order to do a protein crystallography experiment with an electron pulse, you need an emittance of only a few nanometer rad. And while this is easily achievable in a TEM, so a transmission electron microscope in which there's on average one electron at a time inside the microscope. If you want to do this with pulses of many electrons in a single bunch, it's extremely difficult to get there. And a way forward is to realize that this transverse coherence length is proportional to the temperature of your beam. So this you can imagine if your electron bunch has a high temperature, there's a lot of random motion, so you have a lot of transverse momentum spread. and that means that you have a larger divergence angle and a poor coherence length. So what people have done is that they use regular photocathodes from which they extract these electron bunches and cool these down to cryogenic temperatures. Now, what we are trying to do is to push it even further. So what you see here is just to stress the point again that we need a coherence length that is several nanometers. That means that you need an electron bunch temperature that is some tens of Kelvin, so that's very cold. So then I ask you, where do we find the lowest temperatures on Earth? It's not on the North Pole. It's actually in laser-cooled atoms. So what we can do is, this was a Nobel Prize in 2013, I think. What you can do is that with a bunch of laser beams, you can cool down atoms so that they really practically stand still in space. And we routinely achieve a temperature of 0.1 millikelvin of these atoms. So these are rubidium atoms. You get a little cloud of rubidium atoms that are really standing still in space. And then the next step is that we use 2 laser beams to ionize these rubidium atoms. So at the point where these 2 beams overlap, you create a bunch of electrons, which is also practically standing still, right? They are derived from these atoms that were already standing still. And then if you carefully tune the ionization wavelength of the laser, then the produced electron beam is also practically standing still. And then using a DC electric field, we accelerate the electron beam towards the sample. This is the principle of the ultra-cold electron source, something that was pioneered in our group already 20 years ago. And this principle has undergone several revisions. And by now, the version we have in the lab looks like this. I won't go through everything here, but the main point is that here in the center, that's where we trap and cool these rubidium atoms. And then here are these 2 laser beams, and at the point where they overlap, we create the electron pulse. Here in green, you see the electron pulse that gets accelerated into the beamline. And in my lab, this is what it looks like in reality. So you see it's really very, very compact. I bet even more compact than the compact X-ray source in Arizona. So in here, this is where we trap and cool the rubidium atoms. Then, not shown here on the right, that's where my femtosecond laser is, from which the ionization pulse comes. This ionizes these atoms in here. Oh, I should have a, yeah, exactly. What you see here is a fluorescence image of this laser-cooled atoms in here. So if you shine on them with a specific wavelength, you get fluorescence, and you can actually see this cloud of ultra-cold rubidium atoms. So we ionize these, which creates this electron pulse, which is then accelerated onto the sample, which is inside this chamber. And then the diffraction pattern is detected on this direct electron detector. So that is the setup. Some results that we've obtained in the past, well, this is actually already quite old. This was in 2014 on a previous version of the setup, where they did diffraction on a sheet of graphite. I want to repeat this experiment now because I think nowadays we should get much better data than this, but it does show nicely that if they reduce the beam temperature from 250 Kelvin to 10 Kelvin, that you see that the spots become brighter. So this indicates a higher coherence length as you reduce the temperature of the electron beam, showing the principle that I just explained. A more recent result is here from in diffraction from a single gold crystal. But as you know better than me, and then, sorry, what we also did was characterize the bunch length of these electron pulses. So we see that they are quite coherent, but they're also very short. So, so doing a ponderomotive streaking experiment, a previous PhD student measured that these bunches are sub-picosecond short. So that means that you can, if you do a crystallography experiment with this, and you could in principle reach picosecond temporal resolution. So that's about the source, but you know better than me that the sample preparation is at least as important. My proof of principle experiment, I want to do it on purple membrane, which is also where the first crystallography experiments that I showed in the beginning on 2D protein crystals was also purple membrane by Richard Henderson. So I got my purple membrane from a university in Bern, and using a membrane fusion method, I grew them into larger crystals, 2 or 3 micron, and I immediately ran into one of the issues that they were also fighting with in the 80s, which is that these extremely thin 2-dimensional crystals, it's like the plastic foil that you use in the kitchen. It's so extremely thin that it very easily creases. So you get all these wrinkles, which means that then in your diffraction pattern you get all these different copies of your diffraction pattern at different angles, like sort of like a twinning problem, but then like a higher order. But I was lucky enough to run into Richard Henderson himself about a week ago, who gave me some tips to both increase the crystal size and improve the flatness of these crystals. So that's something I'm going to try in the coming months. And that is the current status of the project, where we are actually currently plagued by or limited by 2 important problems in the setup. Firstly, that the electron optics in the beamline at the moment, they are still of rather low quality, which was fine for the proof of principles that have been done until now. But if you actually want to do protein crystallography, I need to solve this. So at the moment, the spot on our sample is on the order of 100 micron, and it means that if you have a 2 micron sample, you waste an unacceptable large fraction of your beam. But we're working on that. And secondly, the electrons at the moment have an energy of 8 keV, and that's very low. So in a typical TEM, it's more 120, 200, or 300 keV. So this limits the thickness of our samples to about 10 nanometers. So that we are also working on, and I will explain this a bit further. The principle is already from 2009. The idea is that we still keep the same source as I've shown until now. So there's first a DC field to accelerate these electrons. That's also what is shown here. This is where these rubidium atoms are, where the electrons are created, and then there's a potential between these 2 plates, which accelerates the electrons. And then they enter these 2 RF cavities, where we, using RF fields, we accelerate the electrons to 100 keV. So this is similar to what you have in any large-scale accelerator. You have these copper cavities in which you inject microwave fields and this accelerates your electron beam. Same thing. And I have a PhD student who worked out this final design. I'm not going to go through everything here, but basically in here is where those rubidium atoms sit, where we create the electron beam. And then here you recognize that copper structure again, where the electrons are accelerated to 100 keV. And it's going in production this month, actually. It's very exciting. And the simulations say, so what you see here is first there's this DC part of the acceleration going up to about 10 keV. And then there's the first acceleration cell and the second one, and we get up to 100 keV. With an energy spread of below 0.1%, and that's really very good for such a system. We have about between 1,000 and 10,000 electrons per pulse, which means that it's not sufficient to do single shot, to get a full diffraction pattern with a single shot. But we're at a kilohertz, so within about 1/10 of a second, you should be able to get a full diffraction pattern. And we conserve the good emittance of the source, so this 1 to 4 nanometer rad, if you remember from the beginning, this is sufficient for protein crystallography. So this should, in principle, do the trick. And I hope that by the end of the year, we should be able to get our first electrons out of this setup, and then hopefully by then I will also have my larger and flatter crystals. And let's say that by our next meeting, I'll be showing the first protein movie. That would be cool. A little bonus. You've seen 2 examples today of Nicoletta and of Pascal this morning, where they combine 2 laser systems in order to scan from very short to very long time delays. In my setup, I want to do something similar, because also bacterial rhodopsin has dynamics from femtoseconds to milliseconds delays. But at the moment, I do not have the budget to buy 2 lasers synchronized to each other. So we came up with a sort of poor man's approach to this. So some of you might be familiar with these multipass cells, which are sometimes used to compress femtosecond laser pulses. And this is based on what is called a Harriot cell. And if you look at the original paper by Harriot, he called it folded optical delay lines, because he meant it as a way to get, in a compact setup, to get very long optical delays. So that's exactly what we also want to use it for. So where in a normal delay line, you can get delays up to a few nanoseconds. With such a configuration, so a master student of mine worked on this, we can scan several delays up to almost 2 microseconds. And all that you need to get for this is basically have 2 relatively expensive mirrors, but say for 10K you can get up to these larger delays. So that was a little bonus. These are the acknowledgements. So I talked about my PhD student working on the DCRF setup and my master student working on this Harriot cell. And we do this in the group of Professor Jon Luijten in Eindhoven. I have the chemistry department. I have these people that help me out with the samples. And as I mentioned, the purple membrane comes from the University of Bergen, Daniel Harder and Dimitrios Vatiadis. And then I'm supported by these 2 fellowships. And that was it. So I would be happy to take any questions. You can take some inspiration from this slide here. Thank you.
Thank you very much for your talk. Take the liberty to ask a first question.
Yes.
How is it with radiation damage? You showed the pulses are a few hundred femtoseconds, but you need multiple shots.
Yeah.
So what is about radiation damage in the sample? Do you have any idea if that would accumulate or like?
Yeah. So it depends a lot on how large you can grow the crystals. But in principle, if you compare for certain cases, if you compare electrons with X-rays, then there's, say, per useful count on your detector, there's, the numbers differ a bit, but between, say, 2 or 3 orders of magnitude less radiation damage if you use electrons as opposed to X-rays. So you, with a crystal that is several microns across, you can get tens to hundreds of diffraction patterns from the same crystal before the radiation damage becomes problematic. That does assume a good detector, which we have.
And the second question would be, if you try to record molecular movies, the samples are still on a carbon support in vacuum, so non-hydrated, or like do you have an idea about hydration of the sample? Or
yeah, no, this is indeed very important. So in our current set up, because the energy of the electrons is so low, 8 keV, as I said, the sample thickness is limited to 10 nanometers. So you cannot have also a hydration layer and some windows in between that doesn't work. But for the 100 keV source, you can do the tricks that they've already developed for TEM, so a liquid cell or graphene layer. And in that case, indeed, the protein is inside a, say, 200 nanometer layer of water, so it's completely hydrated and free to move. Yeah.
Okay, thanks. So I see a few more questions. Petra?
Yeah, Brendan Nenger in my center is one of the innovators of micro-ED, where you take nanocrystals, 3D nanocrystals, and then rotate them in a conventional electron microscope. For these studies now, they had already difficulties growing crystals, nanocrystals, because we are limited even at higher energy to 200 nanometer thick crystals. And the solution which they came up now is to use cryofib to take bigger crystals and mill them. And this will be also a nice opportunity for you, because then you can take a really big crystal, 200 micron long, and just mill it to 100 nanometers, and then in principle measure it. So do you have a cryofib in Eindhoven, and will you try that?
So I have thought about, I've talked also indeed to the cryofib people if this would be a possibility, and they said in principle we can do it. But the thing is, indeed, so you would want to indeed first cryocool them and then FIB them and then thaw them again, bring them back to room, because otherwise how do you get the...
No, they have normally a cryo arm. So that means you do everything and you so you transfer the thin sample practically to the electron microscope, also in the case would be your thing, under cryogenic conditions. So you would have to establish for your system a system how you could get them under cryogenic condition, and because...
Yeah, what I mean is indeed you need, then to get molecular movies, they need to be able to move. So that's why they should be at room temperature.
Yeah, that would be a challenge.
So I'm not sure that it survives the thawing again. Going back to room temperature, I'm not sure that the crystal survives, but maybe it does, I don't know.
I think we have tried it, and the lamella always breaks, but they have now these kind of like jumping board lamella, so they attach it only at one side, and then it tolerates temperature changes and also transport much better.
Oh.
So it's practically open. It's not a closed lamella. It looks like when you're at a swimming pool and you jump in. So it's looking like that. But I think it would be really, really cool to combine these techniques. And I think the best way to get for many proteins really large but very thin crystals would be that cryofib milling. And just one tip we have tried, we have a gallium one at ASU, and it's no use because too much damage to the sample, but they have now these plasma FEBS. And with them you can really much more milder also mill much larger areas.
Okay.
So you should apply for cryo getting a plasma FIB to Eindhoven for doing it. Really cool work. When you have it set up, we would like to come.
Cool, thank you. Yeah.
Yeah, thanks for the nice talk. I'm curious, like, how you would characterize your instrument in relation to the megavolt electron diffraction sources that are available, like the one at SLAC, right? That also has, 2 nanometer radian emittance, so it's got very good emittance and more electrons, and obviously you have better penetration depth at megavolts, and you can pack more electrons into the pulse. So what's your angle? Maybe I'm just missing the sort of unique selling point of yours. Maybe it's cheaper at least, or
it's definitely
are there
cheaper and smaller, because these MEV. So there's indeed SLAC. There's one
at Daisy too.
China. There's Reggae in Daisy.
One in Dortmund, I think. So they're building in the UK as well.
Yeah. So it would still be, I think, an order of magnitude smaller and cheaper, and. So these kind of samples, these 2D crystals, they would actually be too thin again for the MEV beams.
So they were doing graphite at SLAC. So we were shooting like single layers of parafilm there too. So I'm not so sure.
Oh.
No.
Oh, I wasn't aware of that.
Yeah, you should talk to those guys. Actually, they're quite open. I mean, now ZJ is gone. I don't know who's leading the team there, but it could also be worth a visit from your side.
At Slack.
Yeah.
Okay. Yeah. Thanks. Yeah.
Maybe time for one last question I just saw.
Yeah, okay.
Or who else had a question? Okay. Yeah, it was already answered.
Yeah. Naive question, sorry. So why microED that Petra mentioned? Why wasn't it such a problem to get the coherence length compatible with unit cells and microcrystals? And you do have this challenge?
Yeah, because at microED they use a commercial electron microscope, and that means that you have a basically continuous stream of single electrons, and that builds up your image. To do something time resolved with a high temporal resolution, you need pulses. And so the strategy that we take is that we take pulses with thousands or tens of thousands electrons in them, and then you do pump probe like in an X-FEL.
Okay.
So in the normal microED, you cannot get time resolved information.
Yeah, sure. Okay, thanks.